Now, a next curve is a straight line. Now, remembering back to our work on linear functions, we know the gradient of a straight line doesn't change. It's going to be the same value. So if that's going to be the case, it's going to be rising. So it's going to be a positive value. So when we draw it, it's going to be a horizontal line there because it's going to be just one particular value for the derivative. So, and it's going to be positive, so that's why we've drawn it above the x-axis. If we had a straight line going the other way, we'd draw a horizontal line because that would indicate that gradient had the same value the whole way, but because it's the y value is getting smaller, we'd have a negative value. So that's a straight line, how we start to graph a derivative of a straight line. An exponential function. Now, if we have a look there, an exponential function starts out from something really flat. So something that's got a gradient that's not very large. It's positive because it's rising all the way, but it's starting one really small. But then as we go along our exponential function, the graph starts to rise and rise quickly. So our gradient would rise quickly. So if we look at that and graph that, we get something that's small and then starts to rise and rises really quickly, which means our graph of our derivative is also an exponential, which is really a nice way of looking at it. We do a lot of work with this in log and exponential functions and doing calculus applying to exponential functions here, and we see that situation where the curve will rise and the gradient function is an exponential function. So the next one is a log function. This is what a log function starts to look like. So our curve is rising all the time. It's positive gradients. And it starts off rising really quickly, but then starts to flatten out. So our gradient to start off with will be always positive, but it'll be larger. But then when the curve starts to flatten out, it starts to become closer to zero because it's not rising very much. So it's still a positive number because it's rising, but it's a very small gradient because it's getting closer to being a point where it's zero, but it doesn't actually become zero. So that's why we graph that type of function. And you're looking at it going, it looks a bit like a hyperbola. You would be right. It'd be an arm of a hyperbola. This time a parabola, concave down, it rises, it stops at a point, and then falls again. So positive gradient indicating the rise, zero where it turns, and then a negative gradient is represented by values below the x-axis. Again, here's where we were describing before. There's our line that's negative gradient, gives us the same negative value all the way through. So that's why we can graph it just as a straight line, horizontal straight line, because it's going to have the same gradient value all the way through there, and which will be negative. So question 13 here. We've got a straight line here. Now, if my line is neither rising nor falling, then it must be zero because it's not rising, so it doesn't have a positive gradient. It's not falling, so it doesn't have a negative gradient. So it must be having a gradient of zero. So that's why I've graphed the function for this part until it starts to move and rise along the x-axis, because that's where the gradient function would be equal to zero. And then it rises, so it will have a positive gradient. And until it gets to this point, where it turns and goes back down, and that's why it'll go through zero at that point. So it rises, but it eases up. So see how it starts to flatten out? That means our values of the derivative are getting towards zero, and it does hit zero there, and then falls, so our gradient starts to become negative. So that's why we graph it below the x-axis. And our last one here, we're doing the same thing, but a little bit in reverse. So our curve falls and falls and falls and falls till it hits a particular point, then starts to rise. So we have a negative gradient all the way there, but it's getting closer to flattening out and becoming zero. So that's why it approaches the x-axis. Comes zero, because that's where it is zero, it turns, and then rises, so it rises up to a particular point where it becomes just a flat curve. So it rises and it's positive until it hits this point here, and it starts to become the curve along the x-axis, and gradient's going to be zero, because the curve is neither rising nor falling here. So that's why we have it just a straight line along the axis. So there's lots of different curves. um, really, you face a lot of the curves and situations that you're going to see throughout graphing and driving functions and being able to graph them. So have a look through, make sure we can know what our graph look like of the derivative once we see a particular function and what the curve of that function is doing over time.